this session of heat transfer. I am Orinder Mukherjee. I welcome you all to this session. So this is the second lecture. Today we shall be discussing the general heat conduction equation for 3D, that is 3 dimension, and the transient case. Transient means the time dependent phenomenon. Okay, so we shall be discussing the general heat conduction equation with respect to spatial, that is the 3D coordinates, along with transient analysis. Okay, so let us move on to the derivation of the general heat conduction equation for the Cartesian coordinates. Now we will first derive this equation for the Cartesian coordinates, and we will see how this equation changes along with the changes in the coordinate systems. So we'll observe the same equation in the cylindrical coordinates as well as the spherical coordinates. So let us move on to the derivation of general heat conduction equation in Cartesian coordinates. Now let us take into account the energy generation conditions. Now I have already mentioned that energy can't be generated. It is the presence of different heat sources within the control volume which uh, which are taken into account by this quantity which we call as energy generation. So this energy generation quantity can be written as Q dot. Okay, but you have to remember this Q dot is the volumetric heat generation. That means if you want to calculate the total heat generation, then you need to multiply with the volume of this infinite small control volume element. So you need to multiply del x, del y, and del z. I hope you are getting the volume of this cube. So this is a kind of rectangular parallel pipe which has length of dx or delta x, which has a height of delta y, and which is a breadth of delta z. So the volume becomes delta x into delta y into delta z. This is very simple to understand. Now the summation of these quantities, that is the energy entering the control volume, energy moving out of the control volume, and the energy generation. So that sums up to the total energy accumulated. Now how do you calculate the total energy which is accumulated? Now the total heat which is getting accumulated in the lattice due to the heat flow, it can be calculated as the change in heat capacity of the control volume. Okay, now what do you mean by heat capacity? If you remember the concept of thermal diffusivity, then we have already defined this term. So what was thermal diffusivity? It was alpha. We denoted by alpha, and it was the ratio between thermal conductivity and heat capacity. The material which has the tendency of storing energy rather than transporting it, they are said to be less diffusive, less thermally diffusive materials. So this rho Cp refers to the what? It refers to the thermal or heat capacity of the system. So this needs to be also multiplied with the volume, and you are worrying about the change in the thermal capacity for all the control volume. So now you have to remember that this is a time dependent phenomenon. So you need to calculate the change in temperature with respect to change in time. Okay, so this needs to be calculated with respect to change in temperature with respect to change in time. Okay, now let us see how the derivation can be done. So just give me a little bit of time. I will do the calculations and show you in a few moments. Okay, so referring to this equation, you can see that we have written here the energy input quantities or the energy influx, and here we have written the energy efflux or the energy which is going outwards of the system, and this quantity refers to the energy generated or the thermal energy which is transferred into the control volume because of the presence of heat sources like as electrical heating or nuclear fission or ohmic heating. Okay, and this is the rate of energy change, or we can say the total energy which is accumulated within the control volume. Now what I have done here, I have just divided this equation by this quantity, this delta x into delta y into delta z. Okay, now I have arranged this q dot x and q dot x plus delta x in a same bracket, and here you can find we have divided by delta x, delta y and delta z. I have just kept these x quantities in a single bracket here. We have done the same for the y quantities, this the quantities which has the suffix of y. So this is the difference between the heat which is entering and which is leaving, and divided by the the height of the differential control volume. So similarly, we can find we have done this arrangement for the z quantities, the quantities which has the suffix of z, and then we can reach at this value. Now, if if we are interested to find out the changes of this energy for the total control volume, then we need to perform a limit operation. Okay, so we are bothered about to find out the total change over the control volume. Okay, now to find out the control volume, to find out the change over this control volume, we need to assume that this control volume is shrinking into a point. Okay, that means this delta x, this delta y and delta z, they are tending towards 0. So this control volume element can be shrinked to a single point. So that means mathematically how we can think that, that means we have to take some limits. Okay, so we need to take some limits, and these limits will be help us to find out the to these limits will find out to help the total energy change over the control volume. So if we are interested in finding out the limits, so let us take limit delta x tending to 0, and let us apply this for this x quantity. Okay, so q dot x minus q dot x plus delta x dot divided by delta x. Now it is uh, quite easily understood that this is nothing but the differential format. Okay, so with this limit you can find out the derivative of this quantity. Now what will be the answer of this limit? The answer will be minus delta qx dot divided dx. So it will be delta qx dot divided del dx, or the rate of or the change of qx dot with respect to dx. Okay, so this can be written as dq dot x with respect to dx. Okay, similarly this quantity will be nothing but minus dq dot y with respect to dy, and this quantity would be similarly dqz. So that means the heat transfer rate along the z direction with respect to the change in breadth. Okay, so with respect to change in dz. So now as we have understood that, we have applied the mathematical concept of limit, and after implying these limits we can find that these quantities change into this and this. So let us write down the change equation and just find out what are the final changes. So let us give me some time and I will write the equation. So here we can observe the equation which has been changed into dqx dot with respect to ds into dy delta y delta z. Now if you observe these quantities very uh, concentratedly, you will find that this depicts the area in which the q dot x heat is getting transferred. So this q dot x is transferring through this area. Now it is simple. It is very simple. What is the length of this area? It is delta z, and this is your height. So this is a rectangular surface, and you know what are the uh, formula to calculate the area of a rectangular surface. So it is simply delta y delta z. And if you take this heat transfer for this qy along the y direction, then you need to understand this is your surface, right? So what is this? This is delta z. The length of this side is delta z, and this side is delta x. So the area becomes delta x delta z. Similarly, for the heat transfer along the z direction, you will find the area of heat transfer becomes delta x delta y. So after understanding this, we need to find out the quantities of, we need to understand how this dqx dot with respect to dx can be calculated. Now, from the previous discussion, that means what we have discussed in the previous lecture, you can remember that we have discussed Fourier's law, and according to Fourier's law, you know that the heat flux. Okay, so let me write this formula here. So let us take qx double prime as the heat flux. Okay, so this is the rate of heat transfer with respect to the area which is in a normal direction with the direction of heat transfer. So here this the area normal to the direction of heat transfer is divided to the uh, rate of heat transfer. Okay, so that means according to Fourier's law, this formula is denoted as minus k, obviously it will be kx dt dx, right? So if we are interested to find out the rate of heat transfer, then with the help of this Fourier's law, we can easily calculate it. That is kx ax into dt dx, right? Now you will find that in our syllabus this area quantity doesn't change. So we have designed our syllabus in such a format that we'll not encounter such problems where the area is changing. So for a heat transfer surface where the area is assumed to be constant, we can assume that this area is not going to change with respect to the change in dx. Okay, and you will see later on that we'll be assuming this general heat conduction equation for an isotropic and homogeneous material, where this kx, that means the thermal conductivity along x direction, and the thermal conductivities along y as z direction are taken as same. So this is true for an isotropic and homogeneous material. Okay, so these thermal conductivities can change along with the change in temperature and along with the change in the temperature in the three specific directions. Okay, but for an isotropic or homogeneous material, this thermal conductivity doesn't change. Okay, so let it go, but we'll take this kx as for an non-isotropic case. Okay, and afterwards we will see what happens to the isotropic condition. So we are discussing the general heat conduction equation here. Okay, so this ax is the area which is normal to the heat transfer direction in which this qx dot heat is being transferred. So we have already discussed that this is the area of heat transfer, right? So it will be nothing but minus kx dot delta y delta y delta z into dt dx, right? I hope you are able to understand it completely. And After understanding this, if we derive this quantity with respect to dx, then what will be the end answer? So let us use a different ink here so it will help you understand. So now we are interested in uh, performing the derivation with respect to dx. Okay, so we have assumed that this kx, this is the area of the heat transfer, and this is the temperature gradient, right? So dqx dot with respect to dx would be nothing but minus kx. If this kx is defined as a quantity of x, then obviously it will be a conjugate derivative, but we are assuming that this kx is not going to change with respect to the direction of x. Okay, so simply this kx, we are taking this kx as a constant, but if it is mentioned in the problem that this kx varies along with the direction of x, then this should be a conjugate derivative. You have to keep in mind that. So delta y, delta z, and after derivating this quantity, it will be a simple second order derivative. So it becomes del d2t dx2. So the derivative of this quantity with respect to dx becomes minus kx dy delta y delta z into dt d2t dx2. Okay, now if we multiply this quantity with respect to uh, this value here, okay, so it was delta y into delta z, right? So this was delta y into delta z. Then you can understand that these terms, they got they are alike terms, so they so we get rid of these terms, and ultimately the value which you get from doing this operation is nothing but this kx into d2t dx2. Okay, so kx d2t dx2. So this is the second order derivative, right? So let us just remove this. So this is the ultimate result after we have performed this operation. Similarly, we can get the same equation for this term also, and for this term also. So if we are interested to find out these changes, then it will be in the for the y terms, the terms which has this y suffix, it will be d2t and da, I'm sorry, it will be dy2, right? Because we are discussing for the terms which has the suffix y. That means we are discussing regarding the heat transfer which is going in along with the y direction. Okay, and it will be for z, right? It will be kz into d2t dz2. I'm very sorry that I have taken this 2 as the suffix. It will be obviously. Okay, so this this value ultimately reduces to minus kx into d2t dx2. So there is a minus sign here and you get a minus here. So this 2 minus ultimately gives us a positive result. And if we change these values, then let us see what is the final equation which we uh, find. Okay, so just give me some time and I'll write this. So after implementing these values which we have obtained from this differentiation, we get this equation, that is kx into d2t dx2 plus ky into d2t dy2 plus kz into d2t dz2 plus q dot equal to rho cp delta t with respect to delta small t. So this is a change in temperature with respect to change in time. Okay, so now let us assume that this control volume system is an isotropic and homogeneous one. So for isotropic and homogeneous material, okay, so for isotropic, okay, so for isotropic and homogeneous, that means the material has constant properties all along with the control volume system. Okay, so this material will have the same exact properties along with for all over the control volume. So when we assume that this control volume system is an isotropic and homogeneous one, it is quite simple to understand that this thermal conductivity for the three different directions will be exactly same. That is, kx is equal to kz, and we can assume this kx equal to ky equal to kz to a value of. Okay, so now we'll just remove these suffixes. Okay, so ultimately this equation will be reduced to something like this, because all these uh, thermal conductivities which earlier had different suffixes because of the thermal conductivity, because the probability of the changing thermal conductivity along with the different directions, they are now removed, because we have assumed a condition where the material is an isotropic one and the material is throughout homogeneous. That means it has constant properties throughout the control volume. So the equation reduces to k into d2t dx2 plus k into d2t dy2 plus k into d2t dz2 plus q dot equal to rho cp delta t with respect to delta small t. Now if we simply do a division operation, that means we are going to multiply this k from all of these terms. Okay, so what will happen, this k will get removed, this k will get removed, we are dividing, right? So here you will find a k, and here you will also find a k, right? So if you remember that alpha, that was thermal diffusivity, it was the ratio between the thermal conductivity and the thermal or heat capacity. So here you can find the reciprocal of this thermal diffusivity. So this quantity can be written as 1 by alpha, because this is the reciprocal. So it can be written as 1 by alpha. Okay, so ultimately the equation reduces to d2t dx2 plus d2t dy2 plus d2t dz2 plus q dot by k equal to 1 by alpha delta t with respect to small delta t. Now this is very hard to pronounce these terms. Okay, I'm just pronouncing these terms over and over. So there is a very easy way to remember these terms, and here we introduce a mathematical operator which we call as Laplacian operator. Okay, so let us introduce this concept of Laplacian operator, which will help you to understand this concept. Okay, so this is what we mean by this Laplacian operator. Now this is the sign of um, inverted triangle. So you know this is nothing but a Laplacian operator. So this refers to this uh, d2t dx2. So these are the changes of temperature along with the changes in the quantities, or the quantities which by which this cuboid or this volume element has been created, right? So this equation can be simply and in a concise way, it can be written in this formula. Okay, so this is the general heat conduction equation for you. And if you have trouble to understand or remember this Laplacian operator, then you can remember, always remember this format. There is no trouble with that. Now we'll take some special cases, right? Now this equation is valid um, for the three dimensions, as well as it is valid for the transient condition. So if there is any kind of time dependent heat transfer included, so if you find that this conduction is entirely time dependent, then you can apply this formula also. But what happens if the heat transfer is going on in a steady state condition? Now, from the understandings of steady state, which you have dealt in thermodynamics, you know, steady state means that there is no change in the thermodynamic properties with respect to time. That means the thermodynamic properties remain invariant with respect to time. So at steady state, this delta T with respect to delta small t, that means the change of temperature with respect to change in time will be zero, because at steady state the thermodynamic properties, remember, unchanged, and you know temperature is a property of the system. So this equation can be reduced to Q by K as 0. So mind it, this is for steady state 3D heat transfer conditions. Okay, so steady state 3D heat transfer condition. Okay, so in our syllabus we'll be dealing with the steady state heat transfer conditions, as well as heat transfer, or specifically heat conduction at transient conditions also. So it is very important to remember this formula and this formula also. Now if there is no internal thermal energy generation within the system, if there is no heat sources present within the control volume, then what happens? It is very simple. It is very simple to understand that this term Q dot by K, which refers to the volumetric heat generation per unit thermal conductivity, will be 0. So the equation will be reduced to delta 2T, I'm sorry, the Laplacian operator of temperature will be 0. So this is for steady state, steady state. Okay, so I'm just writing the abbreviations here. Steady state, this is for 3D, and no internal, so I stands for internal heat generation. Okay, so there will be no internal heat generation. So this formula will be simply Laplacian operator of temperature equal to 0. Okay, so when the conditions are mentioned as steady state, 3D, and no kind of internal heat or thermal energy generation, specifically thermal energy generation, right? Now in our syllabus we'll be mostly dealing with one-dimensional conduction. Now if we assume this single dimension along the x direction, then these conditions, so what we have done here, we have taken this 3D, we'll take this equation in the 1D format. So we can remove this one. This will be simply written as d 2t dx2 equal to 0. Now remember that we have assumed the heat transfer is going on in the x direction only. If the heat transfer is going on the y direction, then it will be d2t dy2 equal to 0. Okay, I hope you have understood properly the general heat conduction equation for the Cartesian coordinates. Okay, so it was very simple. You have to first understand what are the energy inputs, then you have to understand what are the energy outputs, then you have to consider if there is any kind of heat sources present within the system. You have to take into account for the thermal energy generation within the control volume system, and finally you need to calculate the thermal energy change along by the help of the formula of heat capacity, that is rho Cp into the volume of the control volume element which we have considered, and we have to find the time change, the temperature change with respect to time for this thermal capacity, that is rho Cp into volume into delta T into delta small t. That means the change of temperature with respect to change in time. Okay, so we have dealt with the different cases and conditions of this general heat conduction equation in the Cartesian coordinates, and now we'll be investigating this formula, the same formula, but they will be expressed in different coordinates. So we'll see how this same formula changes along with the changes in the coordinates. So we shall be discussing this generally heat conduction equation in cylindrical coordinates. So just give me some time, I will write the equation here. So in cylindrical coordinates, the temperature will be a function of the radius of the cylinder, that is r, the angle phi, the height, that is z, and the time, that is t. Okay, so whereas in case of Cartesian coordinates, it would have been a function of x, y, z, the space coordinates and the time coordinate, right? So the equation which was earlier del 2t del x2 plus del 2t del y2 and del 2t del z2 plus q dot by k equal to 1 by alpha delta t with respect to delta small t has been changed into this format. Okay, so because of the changes in the coordinates, this equation goes on changing like this. So you must remember this equation, since while describing about the heat transfer in the cylindrical objects we would require the application of this formula. Okay, but generally as we are much more worried about only the 1D heat transfer or 1D conduction, that means a one-dimensional heat conduction problems, so we would require the heat transfer along in the radial direction. So this value or this function refers to the heat transfer in the radial direction for cylindrical objects when we describe this object in the prescribed cylindrical coordinates. So this formula generates like this. Okay, so you must remember this formula, and after we have observed this general heat conduction equation in cylindrical coordinates, let us move on to the next one. That means we will observe the same equation but in spherical coordinates. So this is the equation for you. You can easily understand that this is the term which refers to the heat transfer in the radial direction. So we are describing this whole equation for the spherical coordinates. So when we will be dealing with the objects of like sphere, when we will be discussing the heat transfer or specifically the heat conduction problems for sphere, we would be using this formula. This refers to the internal heat generation or the internal thermal energy generation which we have taken. Now here you can see this k hasn't been divided from this. Okay, so if we divide this term k, then we can get the same form where it would be 1 by alpha, that means the reciprocal of thermal diffusivity. So I hope that you have understood. So again, I would like to inform you that you must remember this term because we will be dealing with mostly one-dimensional heat transfer cases. So this is the term which refers the heat transfer along in the radial direction for spherical objects or spherical system. So this term would be very important and you need to remember it to deal with the heat transfer problems for spherical objects. So we have completed our discussion on the general heat conduction for Cartesian, for cylindrical, and for the spherical coordinates. Now if we find equation, if you remember for the heat transfer cases when it was taken as a one-dimensional steady state heat conduction without any kind of thermal energy generation, then the equation reduced to like this. Okay, so this was for steady state one-dimensional without any kind of thermal energy generation problem. Now always remember that the term which we use as heat generation is quite wrong, because heat can't be generated, any energy can't be generated, but because of the presence of the heat sources within the control volume, we take into account this energy changes by the term energy generation, but energy is never generated. We know from our basic understanding of physics that heat or any kind of energy can never be generated, never be destroyed. Okay, so what I was trying to say, that if we are ended up like this equation and we want to find a solution of this equation, then obviously we need some conditions. Suppose what would be the formula, then we would like to uh, explain this equation in this format. Okay, so ddx of dt dx equal to 0. Then we would like to integrate this. If we perform the integration, then this dt dx would give us a value of constant. Okay, and afterwards we'll find the equation like this: c1x plus c2. So here you can observe that we are ended up uh, with having two different constants. This is c1 is the first constant and c2 is the second one. Now to find the value of these two constants, or such cases where two different constants emerge in our solution and we want to find out the values of these constants, we need to understand the concept of boundary conditions. Okay, so until and unless we do not imply some boundary conditions to this problem, we cannot achieve a specific solution to this problem. So let us discuss what are the boundary conditions and what do we mean by the boundary conditions, and we'll see afterwards how different can be these boundary conditions and how they are written in heat transfer problems. So let us move on to the concept of boundary conditions. So here you can find four different cases. Okay, so since we know that temperature in a certain location can be described as a function of the space coordinates along with the time coordinates, this t is nothing but a function of x, y, z. So these three are the space coordinates and this t is the time coordinate. Okay, so this t can be represented as a function of these coordinates. Okay, now if a constant surface temperature is mentioned and it is given or it is mentioned in the problem, then you can say for obviously a one-dimensional case, it can be written as x dot t. Okay, so we are reducing this term. So since this term was dependent on all the three dimensions along with the time coordinate, here we are reducing this analogy into a one-dimensional time dependent condition. Okay, so at point, so here it represents this x-axis and it represents the temperature axis, right? So at x is equal to 0, at x is equal to 0, the constant temperature T can be written as Ts. So this is a boundary condition. Okay, like previously we had found this equation, if you remember. So if we put x is equal to 0 here, then we will understand that this Ts is equal to C2. I think you have understood this. So now this equation would be reduced to like this: C1x plus Ts. Though we want to find this value, this C1 is still unknown, but we have solved the value of the constant C2. Okay, now let us see. So this is called as a constant surface temperature. That means a constant surface temperature is maintained and this boundary condition is applied here. So this is called as Dirichlet boundary condition. We'll see in just a few minutes what do you mean by that. And here, mm, this is the constant surface heat flux. Okay, so when you know the value of the heat flux, when the heat flux is defined to you, you can imply this Fourier's law, and x is equal to 0. So this, when the heat flux is constant and it is finite, you can imply this formula. So at x is equal to 0, this heat flux will be equal to qs prime double prime. Okay, so you, from Fourier's law, you know this k delta t delta x, but at x is equal to 0. So this is the boundary condition which I am talking about. So it would be qs double prime. Okay, so if we try to apply this formula here, what would be the result? This delta t delta x would be simply c1, right? Because it is a term which is independent of x. So when we derive this t with respect to x, c1 would be the term with which we would be left with. So delta t delta x would be c1, and from this boundary condition which is already implied here, you can find this delta t delta x would be qs double prime divided by, so this c1 at obviously x is equal to 0, it will be qs double prime divided by k. Now here we have found out the value of this c1. Okay, so this is the third boundary condition, or the kind of same one. So I hope that with the explanation of the case of the steady state one dimensional heat transfer case without any kind of thermal energy generation, I hope I have explained to you the applications of these boundary conditions. Now when the surface is insulated, when this information is provided to you in the problem that the surface is insulated, then you can write that there is no heat flux. Since there is no heat transfer going on, obviously there will be the heat flux. That means the change of temperature or the temperature gradient would be 0. That is very simple to understand, I hope. And this is a convection. So when you find that heat, there is a fluid motion over a solid surface, and this solid surface is maintained at a temperature Ts, and the fluid temperature is maintained at Tf, and this Ts, so let me write Ts here because it would cause complications to understand. So this Ts is greater than Tf, so this heat transfer will take place. Okay, now at the interface, some conditions can be some boundary conditions can be implied. Okay, so this is your interface here at x is equal to 0. So you know the heat flux equals to the heat flux by the convection. So the conduction heat flux equals to the convection heat flux. Since we are not acquainted with the Newton's law of cooling, you will not understand this formula, but the concept is that, the physical concept is that, when there is a convection heat transfer going on, you can apply these boundary conditions at the interface of the surface. Okay, and at the interface the conduction heat flux would be equal to the convection heat flux. Now from Newton's law of cooling, this let us just simply write this delta T is the rate of heat transfer for convection heat transfer process. So this is what we know as, uh, this is a very a simplistic explanation, mind it. we are not getting into the details. So this is a simplistic interpretation of the Newton's law of cooling, where this H is the convection heat transfer coefficients. It depends on numerous number of parameters. Okay, uh, this is the area of heat transfer, and this is the temperature change. So the temperature change between the solid surface and the fluid, which is moving with a certain velocity and a certain temperature. Okay, so by Newton's law of cooling, we can define the rate of heat transfer through the convection by this formula. So this is the convection heat flux. I'm sorry, if you know that heat flux means the heat transfer rate divided by the area normal to the direction of heat transfer. So if you divide this equation by A, you will obtain this formula, right? It would be something like, sorry, so it would be something like this, right? So here it has been implicated here. This T infinity refers to the surroundings temperature, and this is the temperature at when x is equal to 0, and this small t refers to the time t. Okay, so this is the fluid temperature. So here you can find out the temperature difference between the two surfaces. Okay, the ambient one, which is denoted by this T infinite or T uh, S. Okay, and this is your surface temperature at the interface, mind it, and this is your conduction heat flux when the x is taken 0. So we'll be understanding these boundary conditions when we'll be dealing with specific cases of heat transfer through cylinders, heat transfer through rectangular slabs, and heat transfer through the spheres. So for today, I will end my lecture here, and for the next class, we'll start with the discussion of one-dimensional steady-state heat conduction for the rectangular slabs. So at that case, we'll be implying these boundary conditions, and I hope that you will understand the applications of these boundary conditions in a much better way. In fact, today I have just laid a foundation stone of the concepts of the heat transfer cases for rectangular slab. I hope you will understand it on the later one in the next lecture. So for today, I would like to end it here. Hope it was an interesting experience for you, and I would like to thank you for your concentration, for as you have listened the whole lecture. So thank you for your presence. Thank you all. Goodbye. See you in the next lecture.